So this talk's on understanding text-to-image models. And a little bit about me. I'm Jose Portilla. I'm an instructor on Udemy with somehow 4 million students. I don't know how that happened. I teach like Python, data science, and machine learning. I'm also the founder of another company called TO Magic, but we'll talk about that at the end. And just want to give you a little bit of background on what this talk is about. And also we'll set expectations. So the title of this talk, Understanding Text-to-Image Models, I'm actually going to discuss like 2 types of understanding. One is just a general understanding of how text-to-image models work. So maybe you've played around with like Stable Diffusion or DALL-E and have been curious like how this actually works behind the scenes. We'll be talking about just kind of an intuitive understanding of that. And then we'll also explore a different type of understanding, which is, can we as humans interpret and understand the model's own understanding of images? But just to set some expectations, who is this talk for? It's for people who are interested in getting a better understanding of how general text-to-image models work, and also how we can have interpretability in their latent space. And I'm going to try my best to avoid equations because I don't think it's super useful to have 10 loss functions there when you don't have pencil and paper. But I should also state that if you already know how Stable Diffusion works, maybe you read the paper and understand it, if you understand CLIP, and especially if you understand sparse autoencoders for model interpretability, this talk might be too basic for you. So just, you won't insult me if you're super smart and just leave right now. So I just want to point that out. OK, so with that being said, we're going to start at a super abstract level and then kind of hone in to try to give you an intuitive understanding of how these models actually work. All right, so first off, it's the neuron. That's what you have inside your head, hopefully. And so there's a couple of parts of the neuron. There's the nucleus, there's dendrites, there's the axon, and then there are the axon terminals, right? So you already have this biological neuron. And then there's a biological neural network because you can just extend these axon terminals to connect to other neuron cells, and then you have a brain, which still has many mysteries of how it actually works, but luckily for us, we can try to create the artificial neuron. So starting from this understanding of a biological neuron, we will create an abstraction for the artificial neuron, and we'll kind of zip through this because we're kind of starting abstract and going into more detail later on. But again, the artificial neuron basically takes in a set of inputs and biases. You multiply that by some weights, and what's important about those weights is during the training process, we can update these right. That goes into a transfer function, which eventually goes through an activation function. You get some output y, and that leads to more neurons, et cetera, and then you have an artificial neural network. Hopefully we're kind of all kind of familiar with this or have at least heard of this before. And so most important, there's specific different architectures of neural networks, right? And one that becomes pretty important to understand during text-to-image models is the encoder and decoder, or these autoencoder networks. So I can connect these neurons to create a network. And for simplicity, instead of drawing out each neuron and each connection, I'll just describe them as layers. And something to understand here is depending on the architecture, we can actually have layers go from a really large input layer to a smaller one. So notice here in this diagram, right, the layers are getting smaller, and so we're somehow encoding information. And so this is actually implying some sort of compression of information. And on the other side of things, I could have a decoder going the other way, right? So I could reverse this with another network, and if I attach these together, I have an encoding and decoding process. Essentially, taking some information, compressing it into some latent space, and then I could decompress, so to speak. All right, so we have an encoder and a decoder. And the reason I mention these now is because towards the end of our talk, we're going to have kind of a closer discussion of trying to understand what's actually going on in this code layer. Sometimes people also call it the Z layer. Basically, if you're able to take all this information and compress it to something, can we actually understand what's going on there? So then a couple of questions to be thinking about is what information is actually being captured here? Especially when we think about text-to-image models, it would be interesting to try to understand with millions of images that these sort of models are seeing, how is it that they're able to compress to like a very small amount of data relative to everything they've seen? And is it possible for humans to actually interpret this code layer using something like a sparse autoencoder, which we'll discuss later on? OK, so far we learned about biological neuron, go to the artificial neuron, and then I can set up an architecture for this like compression, decompression idea. And most importantly, there's like something interesting going on there, right? OK, so keep that neural network architecture in mind as we explore the general idea of text-to-image models. So text-to-image models, really what they are is usually an assembly of a bunch of different components. And so we're going to break it all down step by step here. And again, I'm going to start with like a really high-level abstraction, and then we're going to keep diving deeper and deeper until we have hopefully a good intuition by the end of this talk on how these models work. And then once we do that, we'll dive deeper into the latent space of these models, and hopefully then we can get an understanding of how we can interpret the model's understanding of visual space. So again, kind of the two types of understandings that we're going for. So at a really high level, what is a text-to-image model? We know that we take in some text, like a sketch of a puppy. We feed it into, right now, which we'll kind of think about like a big black box. And if everything works, we get the relevant image. So what we're trying to answer now is, can I get an intuition for what is going on inside of this like magical box that you sometimes play with if you open ChatGPT and say, make me a sketch of a puppy? So first things first, we need to understand text. And if you've ever played around with ChatGPT or large language models, you may be familiar with this idea of text tokenization. And if you were trying to follow along with text tokenization for text-to-image models, there are some things that apply and then some things that won't really apply. So I could take this text string, and I could start doing things like adding a start and stop token for just simple notation of when I'm starting the prompt and when I'm ending the prompt. And then I could try to be a little more clever, and to make sure all the prompts are of the same length, I could have like cutoffs, or I could have padding, essentially just like emptiness, to make sure that all the text prompts are always the same length. So for example, I believe the original Stable Diffusion paper set a length of 77 tokens. And then, again, depending on your experience with large language models, you might be thinking, hey, computers can't perform calculations directly with words, so I need some sort of numerical representation of these tokens. And for simplicity here, I'm going to remove this idea of like padding and start and stop tokens, but just keep in mind that they're technically there. And so you might be thinking from an LLM perspective, oh, I'll just try to directly transform these into vectors and get my text token vectorization there. Unfortunately, if we think back to kind of the original publications of these text-to-image models, that actually won't be the correct approach here, because I don't just need text. I actually need some linking between text and images. And this is going to drive the motivation for our first component. So that, just by itself, for this kind of first iteration of these Stable Diffusion type models, isn't enough, because we need to connect this text prompt to some sort of visual image output. So the problem is, where do I get this sort of training data set? I need a bunch of text and image pairs. And by a bunch, I mean on the scale of like 400 million pairs. And it would obviously cost a lot of money and time to manually create and label this data set. Luckily, the folks at OpenAI figured out a solution, along with other people. They also figured this out. The internet is actually full of images already for us, millions of them. And a lot of them already have what's known as an alt tag, which describes in text what's found in the image. So if you're visually impaired, you could listen to this text and understand what's actually going on in the image. So in 2021, which on the scale of AI is like ancient history now, which is kind of crazy, OpenAI publishes a paper that introduced CLIP, which you may have heard of. It stands for Contrastive Language Image Pre-training. And to be clear, CLIP by itself is not a text-to-image model, but it's going to be a component that we're going to use to build out like our final big text-to-image model. Really, all it is just a network that tells you how well a given text caption matches an image. And later on, we'll see that one of the results is going to be a way to embed text that works for text-to-image vectors. So let's quickly discuss OpenAI and how they trained this kind of first iteration of CLIP. So what they realized is, hey, the internet is full of these text-to-image pairs. And so I can grab one of these pairs, and I can think about training two separate encoders that I'm going to somehow link. And this is why we discussed like encoders and decoders earlier. So I'm going to have one text encoder and one image encoder. And then that's going to produce some sort of vector output or embedding. And what I would really like is to link the training of the encoders so that the embedded outputs are very similar when the text-image pairs are correct and they match. So again, if I have a correct text that describes this image, I would like these to try to be very similar. Likewise, if I have a text that says like photo of a man, but I actually have a picture of a cat, I also want to link these so that they're very different for quote-unquote incorrect pairs. And the way they would do this in training CLIP is they would batch some images together and set up a batch of both the text and the image pairs. And you can set up a matrix to then measure cosine similarity between the vector embeddings. So you have a bunch of text strings that you encode to some vector representation. And then you have a bunch of images that match up with these that you encode to some image embedding. And what you're going to do is you're going to end up assembling this matrix. And then the training process to update these weights is along the diagonal. This is where they actually correctly match. Image 1 to text 1, right? Image 2 to text 2. That is what you want to be very similar. And you want everything else to be dissimilar. And so throughout this training process, again, this takes many, many, many images. But you're essentially going to have embeddings linked both in text and image space. Now, just to give you an idea of what kind of downstream applications you can have with CLIP, is you could build an image label classifier now that you have this trained CLIP. So for example, what you could do is you could construct a bunch of text strings, for example, that said, hey, picture of a blank, like picture of a boat, or picture of a dog, picture of a cat, etc. And so you have a bunch of just like strings that you constructed. And if you wanted to build a kind of crude image classification system, now that you've trained CLIP, you could encode these into embeddings, essentially creating labels and a corresponding vector for each one. So you would get something that looks like this. And then, if you had an image that you wanted to classify, you would pass that into your trained image encoder. This is now just a single image. And then you would see, hey, based off those similarities that I trained on, can you find the label embedding that is like most similar with CLIP? And now you kind of have trained a classification system just with this idea of matching these text encoders with image encoders. So very useful stuff here. For our use case, we're most interested in this text encoder that has some connection to images. And the actual vector from the original CLIP paper, I believe, is 77 by 76 or 768 dimensions. And later on, we're actually going to use this text encoder to create useful embeddings from raw text strings. So that's kind of component number one that we had to realize and construct. And this was actually like a separate publication before like DALL-E came out. OK, so we now have a way to link text and images via an embedding vector space. And so now let's take a quick detour to another component that we're going to need, which is understanding what's known as the diffusion process. Not to be confused with Stable Diffusion. Stable Diffusion is just like this name they attached to this whole model. But I'm actually specifically talking about this diffusion, sometimes known as a denoising process. And so we'll consider that separately, and then we'll kind of attach them all together. So later on, we're going to need some way to generate an actual image. Like from our perspective, that's like a 2D square of red, green, and blue channels. Technically speaking, it's like a 3-dimensional matrix, right? Because you have 1 dimension for red, green, and then blue. But in general, we need to start from something, for humans, that is, that's like, OK, here's this image, and then make it into the correct image. So what we could start with is an image of noise. And if you kind of glanced at these papers, you kind of have some understanding of like, oh, OK, they're like doing some sort of denoising. But how do we actually train this model to remove this noise. A quick note on this diffusion process. What I'm about to show you is denoising in the pixel image space. This is known as DDPM, or denoising diffusion probabilistic models. That was like one of the original papers on this. I would say most modern or current day models would not do this because you would just actually run the denoising process on like a latent space representation of the image. But that's not really pretty to visualize, and it's way harder to like have an intuitive understanding of denoising just random numbers. So I'm going to present it as the pixel image space, which kind of lines up with kind of early 2020s models. So just a heads up on that. A lot of the stuff that we're looking at is kind of more from a historical perspective, but I think it's easier to build the intuition on those sort of models rather than just jumping to like the latest transformer. Okay, so we can think of the diffusion process as creating visual image information to try to go from a noise to an image. So how does this actually work? First off, we need to create our training data. So this is actually pretty simple. I can take an existing image and add some Gaussian noise to it, and then take that, add a little more Gaussian noise, and I can actually continue to add this noise at a prescribed schedule. So maybe you've heard this term, scheduling on noise. This is where it starts to come from. And so we can think of the noising and denoising process as happening over some number of time steps t, where t0 is like your original clean image, and then you slowly added more noise over like t amount of steps. So one way we could think about denoising this is because of this schedule, during training on example image data, we don't actually need to go in the entire order t. And I'm going to kind of start off with the most intuitive understanding of denoising, and then we'll start introducing more and more tricks that reflect the actual reality of the original Stable Diffusion paper. But remember, I'm doing this in steps and adding like the same amount of noise at each step. I could just skip straight from T0 to T4, right? If the way Gaussian noise works, it's really easy to just say, okay, sum up all this noise and then just jump straight from T0 to T4. And since we know how much noise is being added at each step, I can easily produce a training sample for any time step. So that's kind of key idea number one. And so our goal right now is to train some sort of diffusion model that can take an image and any time step and produce the next image at t-1. So it's kind of base level. And then we'll introduce a trick that actually improves on this. So I would like to go from like t to t-1, or t of 3 to t of 2. So if I have t of 4, so I have an image and its known time step, I'm going to pass this into some sort of like autoencoder network, more on that later. So I could start training and creating a model that takes in the image and the time step, and instead of trying to denoise the image directly, it's actually mathematically a lot easier to try to predict the noise that needs to be removed from this image. So that's also like a critical insight that this just works out to be much more robust, where these models actually kind of ironically produce noise that you yourself will later remove from the image. So given a time step and an image, you produce the noise you think that you should remove to get to the next time step. So here we have the noise, and then I could take that noise, subtract it from that image, and if everything works well, I would go one time step forward. So that's kind of thinking, I guess, level one, so to speak. But if we're more clever about this, and we'll start to kind of reflect what actually happens in the paper, it would actually be a lot better if I could just train the model to try to produce all the noise that could be removed to obtain the original image. So you actually end up creating an even more robust model if you say, hey, instead of trying to predict from like T4 to T3 or T20 to T19, just for any time step, try to go and give me the noise that gives me all the way back to the original image. So now you're actually building a model that can take a noisy image, and it's going to attempt to produce the noise that could be removed to jump all the way back to T0, instead of jumping like step by step by step. So ideally, if this worked in one shot, you would get back the original image. But keep in mind, it's likely that the model is not going to do this perfectly in one shot. There is a lot of work to do like one-step and two-step models, but for right now, we're in the early 2020s, I guess we still are, but very early 2020s in the thought process here. So because it's not going to be perfect in its prediction, but you already created a robust model that always tries to go to the original image, what you're going to do is you're just going to keep looping this process. Now you have the estimated output. You'll take that, feed it back in, and again, you're always trying to jump to the original image. So that will produce some noise. You repeat this process, and this ends up being a lot more robust and a lot more stable. So kind of the key insights here was the fact that for creating training data, it's super easy to create training data at any arbitrary time step. And also, it's actually much more robust if you try to jump all the way to the original image. And then finally, third point, is these models are actually producing noise that should be removed. They themselves are not, like, in theory, denoising the image. They're giving you the noise, which becomes important when we actually start putting this all together. The fact that we produce noise will be very convenient for CFG, which we'll see later on. OK, so far it seems like we only created this like noise creation / noise removal model. That could be really useful in a lot of situations. Like if you had a really old corrupted image, you could just straight up use that model and clean up the image. But we haven't really yet seen how to incorporate that text encoder from clip to help create an image from a text prompt. So to condition our network on text prompts, we're going to need to incorporate that text embedding, which remember has been trained to be linked to images. Very useful. And there's also a variety of other models beyond clip, but we'll use clip because it's kind of like the grandfather of all this. And then we're going to also discuss classifier-free guidance, or CFG, which you may have seen this term if you've played around with some of these models. And that will actually help us align the output to match the desired text prompt. And then we can also adjust that encoder and decoder to a UNet architecture. So remember, I described the fact that we have some model that's producing that noise to be removed. In kind of the old school original papers, they decided they would use a UNet model, which has a lot of success in other computer vision tasks. And you can think of it as like a slight adjustment of the autoencoder we previously discussed, where we actually incorporate what are known as convolutional neural networks for downsampling and upsampling. And then yet one more trick we do with the UNet model is we actually provide what are known as skip connections between the downsampling and the upsampling to try to preserve details. And when you're drawing these connections between these layers, the diagrams kind of force you to draw this as a U. All right. So now we have our choice of model. This is where like the latest iterations of text-to-image models will choose something else. But this is kind of the old school UNet model. I have learned from my previous talks not to try to discuss the latest models because like in 24 hours there's a new model. So better to look into the past. OK, so how do we combine these? And how do we actually use CFG? Well, we're going to combine a text encoder and a UNet for image generation. So we have this noisy image, and then we also have our desired text, like photo of a dog, a picture of a man, etc. And then we have that text encoding, which has specifically been linked to images. And then we're going to train this architecture to hopefully produce the noise that can then be removed to then create the image. And we want to align it to this text encoding so that it matches the desired output. And you could keep looping this and then produce the noise, remove the noise, and here you have your text-to-image model. Now, unfortunately, when the original researchers were creating this, they discovered this by itself actually doesn't work too well. If you wanted a picture of a house, you would get kind of these weird artifacts and noisy images. So even with the inclusion of that text embedding from clip, the results won't be that great. But there's still one more trick that they figured out. Many more tricks, but we'll discuss this one. Is we can actually measure the impact of the prompt by running the network again with an empty prompt to produce essentially generic like image noise. So here's the trick. You're going to run this twice, once with your desired prompt, and then once with your empty prompt. So what does this actually look like? Okay, so you have your text prompt and the image you're trying to figure out how much noise there is. And so you have your prompt noise. So I say like sketch of a house, I run this whole process, and I have the noise I would like to remove that's attached to my text embedding. Then what I'm going to do is essentially run an empty prompt, like an empty string, and then I will have my generic noise. And this is the trick for CFG, or classifier-free guidance. So essentially what you have here is you have two sets of noise. The first one you created with your text encoding. So that's the noise that's related to following the text prompt. Then you have what we will call like generic noise. And this is just noise related to get what you could think of as a good quality image. Essentially, because you didn't provide a text embedding, the model is just trying to push it so it matches the sorts of like images it was trained on. Granted, that's like millions of images, but it's just trying to match good images versus trying to match your particular text embedding or text token. So now that you've run this twice, and you have two sets of noises that could potentially be removed, what you can do is take your prompt-specific noise, subtract that generic noise, and you almost have like this prompt impact noise. So this is noise that should be removed specific to your prompt. Now, it's up to you how much you want to use this noise. So the final like formula, so to speak, for this trick is you have this prompt impact noise that you just calculated, and it's up to you to multiply that by some sort of scale, then add back in that generic noise to produce a generic good quality image, and now you have the final noise that you will try to remove from the image that you've been creating. So a couple of caveats here is that you realize you have this balancing act between how well do you want to match your text prompt versus get a good quality image. And if you've ever played with these like services that allow you to up the CFG scale, if you go way too high on this, you get what are known as like deep fried images, which are just like highly saturated images. And if you go too low on the CFG scale, you'll get a good image, but it won't be too related to your text prompt. So it's a balancing act between how well you adhere to your prompt versus how well you produce like a quote-unquote good-looking image, essentially an image that matches your original data set. But at the end of the day, we've combined all these components, and you've created a text-to-image model for image generation. And you now have this little like formula here of CFG scale. You can edit how much your prompt is actually impacting everything. And then you can start looping based off this final noise. And then hopefully at the end of the day, you've produced an image that you like. And there's one more step here. There is technically an upscaler that happens. So the very last step is to upscale your image. And this is actually quite a simple network. You basically train it on low resolution versions of high resolution images. So you'll go from like 512 to 1024 by 1024 pixels. And that's kind of the last step. Okay, so if everything went well, hopefully you have a better understanding now of the basic ideas behind text-to-image models. And again, something to keep in mind is there's been many improvements and upgrades to every component we've discussed. This is kind of an older architecture, but hopefully it was getting you a good intuition. So you now have an understanding or intuition of how the text-to-image models work. But now to the second part of our discussion is kind of understanding the understanding. So although we understand the general idea of the text-to-image models, is it possible to understand what the model understands? Specifically, remember back to our discussion of this autoencoder. We've seen this idea that they kind of compress information. So what if instead of compression, we actually tried expansion, and we tried to create a super sparse matrix? So remember, or recall, from just a few minutes ago, that Clip is producing these pretty complex embeddings. And these complex embeddings can be kind of thought of as the sum of like many ideas. So if you have this like embedding vector during the Clip training process, what could actually be happening behind the scenes is this embedding, like Paris, is actually the sum of many ideas that you don't really get access to. Like, it's France. It also has to do with city. It also has to do with nouns, etc. But unfortunately for you, as a human, it's really hard just to look at like a weight or a particular set of neurons and be like, oh yeah, that's clearly the sum in the latent space. Like, we just don't think like that. So this is where the idea of a sparse autoencoder comes into play. So remember, you have this like compression nature of these autoencoders, and we see that single neurons get activated by mixtures of multiple concepts. Because you're going so dense and you're compressing so much, the neurons are doing heavy lifting, so to speak, but they become what's known as polysemantic. And this is actually kind of what you want, that one neuron can be activated by multiple concepts, so you don't have too many duplicate neurons. So one neuron could be trained to be activated both on human faces and buildings and cars, etc. That's great for efficiency of the models on a computer. So you have like these really dense latent spaces. Makes it much easier to run on hardware. But from a human perspective, not super great to see like these super dense neurons in this space that then you have really hard time interpreting. So instead, you switch it to go the other way. Instead of polysemantic neurons, that is poly, multiple, semantic, meaning, so neurons that understand multiple meanings, you would actually kind of want to go to monosemantic. So you have like one neuron that only represents like one topic, or one set of neurons that only represents one topic. And from a human perspective, that would allow us to better understand which cohesive concepts actually activate the neurons. So this is where we use a sparse autoencoder, which are very popular in the field of mechanistic interpretability and being able to steer models to particular outputs. So SAEs is actually a really simple concept. It's a super shallow encoder-decoder, but instead of having a very compressed layer in the middle, you actually want it to be very sparse so that only a few neurons are activated. And so this is a little bit of a simplification, but the general intuition is there, that if you had a sparse autoencoder to try to take in a clip embedding, go super wide, and this is just a visualization, like this would be much larger than whatever the 9 neurons I have there, and then try to reproduce that clip embedding back out, only a few neurons would need to get activated for the clip embedding. And this is more on like the image encoding side of things. So how would this actually like intuitively work? Well, if you've trained this sparse autoencoder to have a bunch of monosemantic neurons, that is, only a few neurons get activated because it's so large, it doesn't need neurons doing like heavy lifting of multiple concepts, you could begin to explore images that activate particular monosemantic neurons. So for example, here you can see all these images are different, right? Blue paint, blue fish, blue rocket ship, but they all kind of have this idea of blue. And so if you were to feed that into your sparse autoencoder, you now are lucky that there's so many neurons here, only a few are getting activated, and intuitively as humans, we can start thinking of these as like the blue neurons. And you could repeat this process for different batches of images. So for example, you could have a bunch of images of houses, and one is like a sketch of a house, one is a cartoon, one is a photo, but it doesn't matter because it's so sparse, only a few neurons are going to be activated, which we as humans can interpret as, oh, these are like the house neurons. Because only a few are getting activated, you could perform some like fancy mathematical tricks to try to weigh these actions even heavier during the embedding process. So you can almost make this embedding to be very like house-like. From an actual pragmatic perspective, it's sometimes difficult to interpret what like category is actually being activated, but you as a human can kind of just tell, okay, I would like to steer it to be more like these images, to be more house-like, or more cartoon-like, or more blue, etc. So now you can actually start to build an understanding of what the network embeddings understand, because this will actually allow you to steer your results to use images rather than just words. And this is ideal because it's often easier to describe your desired image with another image. If you were working with a Photoshop editor or like Adobe Illustrator editor to create a desired image, there's only so much you're going to be able to tell them via words. Eventually, you're probably going to pull up some image and, oh, make it more like that. And this visual steering with these sparse autoencoders actually allows us to do just that. So to give you some real examples, typically you would say, OK, give me a photo of a man, and you produce a photo of a man. But if you wanted to perform visual steering, you could perform what is essentially an intervention on the original clip text embedding. So you could use that sparse autoencoder to ascertain an embedding from desired images. And optionally, you would label this category for future use. So you could be like, hey, these are like the blue weights or the house weights, et cetera. And you can then increase the weight of that desired effect based off that sparse autoencoder, and then intervene with a new embedding to regenerate the image based off that sparse autoencoder embedding that you created. So again, instead of just having this image of a man, what you can do is have a bunch of images that you would like to kind of weigh the steering towards. So here we can see a bunch of images, and the kind of theme that a human would take away from this is not that they're blue necessarily, but that they're all like a blue background. And so this is actually like a real category from a real like sparse autoencoder trained on clip embeddings. And if we take this, then I could say, hey, these are the neurons that are getting activated. It's a lot easier to see now that they're more monosemantic. I can try to like up that weight, rerun the generation with my new kind of visual steered embedding, essentially this intervention. And instead of this image, you will actually get this image. And you'll see that like the look kind of appears the same, but it visually was steered towards a blue background. And you can now do this for like any group of images with this sparse autoencoder visual steering. So you could grab a bunch of images that are related based off like a white cowboy hat, increase that, and then intervene again with this like white cowboy hat embedding without having to say, put this man in a white cowboy hat, and it will start to edit and adjust. And obviously, details change, but you can see that this is just on the visual side of things. You're not actually updating the text. So that allows you to basically have a better understanding, so to speak, of what the model understands, because now we have these new mechanisms for visual steering using images, which is how we as humans would think about text-to-image software, so to speak. And that kind of brings us to what we're working on at TO Magic to kind of sum this all up. There's actually much better ways of doing this. So what I'm working on now is developing ways, for children to be the star of their own story. So you can take an image and then apply a bunch of interventions, so to speak, so that you can have them be anywhere in their story. You can stay updated at tomagic.com. And yeah, that's kind of it. Hopefully you got a good intuition now of how text-to-image models work, and also hopefully introduce you to this idea of sparse autoencoders for mechanistic interpretability. You can follow me there at those links. But yeah, that's basically it. Thank you.
OK, question time. If you have any questions, you know the way it goes. Just raise your hand and you'll have the microphone. We have some. Yes, please. Here is the fourth row. Yeah. Here it comes. Thank you.
Hello. So where you were showing us how we remove basically noise from the image to get to the final image, we have to start with something, right? So how do we pick the seed image that's the starting point? Is that something that's baked in and always the same, or?
It's just, your starting is always like just pure noise.
Okay, and it's always the same. We don't have an ability to change that or influence it.
So if you're familiar with like seeding random numbers, you could seed a random 2D picture of noise, right? Okay. And so that's what you can use. And so if you ever use these models and you could provide a seed, that's what's actually setting, that's what the seed sets. That's why that allows you to have repeatability in the results, because you started from the same like noising process, so that doesn't change.
Okay. And ideally, if it works right, like every seed is gonna produce almost the same image because we're just removing stuff, getting to a very similar image. So
exactly. So in an ideal world, with everything else staying the same and the seed staying the same, it should be 100% reproducible. Yeah. But if you want to start playing with things like the CFG number, it'd be a good idea to keep that seed the same, so you're starting from the same image, so you know the only change you're affecting is CFG.
Okay, thank you.
Yeah.
Do we have another question? Is there another question somewhere? Yeah, please, sir.
Hi, thanks for your talk. I want to ask you about the sparse autoencoder approach. Did you also consider it for search applications? Because maybe, okay, you could use the original clip vector, dense vector for search, but potentially it could be useful to have the sparse representation and use the sparse representation for search. I'm not sure how many neurons you're activating in the sparse vector, but I mean, for search in general, there are solutions which combine sparse and dense vectors, right? So I'm wondering whether you considered also the sparse representation for search applications.
Some people are working with that. I would say there's actually a lot more research in sparse autoencoders for pure LLMs. And there's like some good startups on this, like Goodfire is one of them from like some ex-Google DeepMind folks. And for whatever reason, a lot of the sparse, well, it's not for whatever reason, it's just like a lot more people use LLMs than text-to-image models. And so steering the LLMs to have particular outputs is where a lot of this research currently lies. And I think there are some search applications there. But there's actually, I haven't seen too much in the, to be like very formal about it, sparse autoencoder mechanistic interpretability space for visual models. But I've seen a ton of research on the text models, which makes a lot of sense because it'd be really nice to just say, update this monosemantic neuron so it's always like business polite or something. And those sort of startups actually have a lot of funny demos, like there's a pirate neuron, so you can update it so it always speaks like a pirate or something like that. And something else that's kind of interesting about the sparse autoencoder space for image models is, for whatever reason, they tend to work really well with clip, but these latest larger models like Flux tend to have a harder time doing the interventions. And it's unclear if that's just because of the different architectures or if they're just so much larger, more training is needed to create that sparse matrix. But what I just showed you here was with clip, which is technically like the old way of embedding, but it's a lot more effective for visual steering. But who knows, maybe like in 6 months that will be totally done. I don't know. It moves so fast.
Thanks.
Yeah.
We have time for one more question if there is another question. Yeah, here in the first row, lady.
First of all, thank you so much for your excellent explanation of dictionary learning. I've heard about it mostly from the LLM side, as you just mentioned. I'm curious if you know of any tools or open source platforms for getting started with visual steering and learning more about it.
I'll have to remember the exact post. It's on lesswrong.com. There is an open source set of weights for visual steering, which is what I used here for the sparse autoencoder. It's by, I can't remember his last name. It's by Gitis, who I know. I'll look it up on my phone and like come find you and show you. Yeah. Sorry for everybody else, I don't know. If you look up sparse autoencoder clip embeddings on Google, it's probably the first hit. But there's an open like collab notebook that allows you to play with it.
Maybe we can spare time for one more if there is anybody else. Yes?
So I guess at some point, if you add too much noise, like you lose all the information from the original image, no?
So, sorry, I can't quite hear the question.
Sorry. I said, I guess for the training part of this denoising process, if you start adding too much noise, at some point you lose all the information from the original image, no? So is there like a T value at which you cannot retrieve the original image anymore?
I think I understand. So you're asking just on the noise scheduling process, can you go too much and like have so much noise that you'll never get something good, essentially? I will say, what I showed you is kind of, again, like old school, early 2020s, which like we're basically in, like 1 or 2 years ago. But the latest research from OpenAI goes around what are called LCMs, or latent consistency models. They actually just recently published a paper/blog post on it, maybe like a month ago. And basically nowadays, the models can do that jump in 1 to 2 steps. So it's not so much an issue anymore of adding too much noise. And I'm not sure that was ever really an issue, because if you go slow enough, you can always denoise. It's more of a balancing act between matching your text versus your image. And I will say a just general challenge in this space is that it's very hard to get good metrics on that match, right, for a new image. So if I asked you, or if I asked one model to create a photo of a house versus another one, it's kind of hard to say like, oh, that is better than that, right? So then you end up kind of in this world of like super complex text embeddings of like, okay, 8 clowns juggling, I don't know, 5 balls or whatever, and then you count and see how well it matches. But I would say the denoising process is, from what I can see in the published space, is getting close to being like a non-issue of like, hey, I'll just do this jump in 1 to 2 steps and like instantly get the image. But LCMs from OpenAI is what you want to Google to get more information on that.
Thank you very much. I think we'll finish up here with the Q&A session. And thank you very much for joining us. This is for you. Thank you.
Thank you.